Yep.
The problem is fixed.
Okay. Could you check it now? Do you hear me? Maybe now you should hear my voice, hear my
We'll
speech.
hear it after a little delay, so let's wait for a couple of seconds.
Uh, Maybe I should mute my microphone on the Google Meet. For example, now, if I switch it off, you should hear my voice from the LinkedIn. Uh, any suggestion?
Yeah, so everything's okay right now on LinkedIn live stream, so you can go on.
Okay, let's continue. Okay, second one, a famous platform is Raspberry Pi. Our lesson will.
And can you please turn your microphone on Google Meet so we can hear you as well?
Okay, okay. Raspberry Pi is the computer for development robotics. Also, it more cheaper than NVIDIA. Okay, real robot assembly parts. Our robot consists from control board. Our control board is based on Raspberry Pi 5, ultrasonic distance sensor, motor driver, and motor wheel. Robot operation system. A robot operation system is a set of software libraries and tools for building robot applications. Last version of robot operation system is a Jazzy. It has a lot of documentation, and we developed our robot based on the robot operation system. Next one is Foxglove. Foxglove helps robotics teams to explore, collaborate, and make sense on the robot's data. Mostly it used for visualizing our data. It helps us record data, ingest it, process data, visualize, and collaborate with it. Next one is the basic knowledge about robotics is a coordinate frame. There could be two kinds of coordinate frames. First one is the global frame and second one is the local frame. In terms of robotics, each robot has its own local frame and it has 3 degrees of freedom. Red one, x-axis, always points to forward of robot. Green y-axis points to the left of the robot, and blue z-axis points up to the robot. Okay, the obstacle avoidance algorithm itself, how it looks. The idea is simple. Let's consider our robot platform, and if there is no obstacle in front of the robot, we set linear speed x equal to 1. It means that the robot start move forward at the maximum speed. If obstacle appears in front of the robot, for example 50 centimeters, we set linear x speed equal to 0 and set angular speed z equal to 0.5. It means robot stop moving forward and start rotating to the right. This is the simple algorithm in the condition if else. That's the whole algorithm. Let's begin to implement it. If you have any questions, we can answer on it. If you don't have any questions, we can move forward. Okay, let's move to the real example. We have our code located on the Git repository. Let's clone it. For this purpose, we copy it. Here we are. Okay. We open terminal. Mux -s demo. Okay. cd home directory, clone our repository, let's find our, anybody remember the password? No? Okay, let it be for once. Okay, we clone it, go to our repository. Next one, we need install dependencies to build our packages. The ROSDEP is the program that collect all dependencies and install it for the robot operation system ROS version Jazzy. Okay, all required installed successfully. Second one is to build packages that need to run our robot. We need 3 packages: ultrasonic one, obstacle avoidance, and motor driver. Let's quickly review all these packages. First one, ultrasonic. Ultrasonic measure distance and publish it with the message called range. It simply writes distance to the obstacle and publish it via robot operation system. This is how it looks. Second one is the obstacle avoidance package. It publish twist message and listen the ultrasonic, read data from it, and make decision. Should it be move forward or starting to turn right? And last one is the motor driver. It creates subscription to the obstacle avoidance algorithm, read values linear and angular speed, and check if linear speed is positive, it moves robot forward. Otherwise, if angular speed non-zero, it move robot to the right. Okay, all packages built successfully. Let's go to the first one. We should activate our environment. Local setup, wash, okay. And next one, we should connect to Foxglove to visualize our robot data. First one, we should make connection between our robot and our laptop. Go to robot, go to robot. For this, we open terminal. Open terminal, go this robot, SSH RPI. Now we connect it to the robot and run WebSocket on the robot side. This WebSocket publish data on port 9090. Okay, then we go to our laptop and make SSH tunnel from robot to our laptop. Okay, go to our terminal on our laptop. Okay, SSH tunnel created, and then we can go to our Foxglove. And make connection. Open connection, select ROS bridge, localhost 9090, open connection. Connection established. We see the URL, timestamp. Okay. First one, let's check which topics currently published. Let's remember that we not run any packages, so far on the robot side running only three default topics: ROS API, ROS API params, and last one, ROS bridge WebSocket. This is WebSocket that we just recently run to make connection to the Foxglove. This WebSocket connects robot and our Foxglove. Okay, let's back to our presentation. First one, we need to run ultrasonic distance sensor. For this purpose, we should create run ROS2 run ultrasonic publisher node. Okay, it started. We can go to our Foxglove and see that there appears new topic, ultrasonic publisher, that published message called ultrasonic range. And we can see what kind of data it sends. So we can split this panel. For example, split right. Let it be here. Change our panel to the plot. And select values. We select the topic ultrasonic range and value of max range. Now we hear this blue line. We can also add another one measurement, ultrasonic range. So now we see two lines, blue one and orange one. Actually, this is a measurement of the distance between robot and obstacle in front of robot. And blue line is the raw measurement, orange line is the measurement that filtered by Kalman filter. But let's discuss it a bit later, just to understand these values. So if I move my hand in front of robot, we see that this measurement decreases approximately 25 centimeters. If I start to move my hand back far away from robot, we see that this distance increases. So this is a great tool to visualize what kind of data we receive from different sensors, for example from ultrasonic sensor. Now it approximately 50 centimeters. It can be decreased. If I move obstacle, it can be increased if I move far away from the robot. So in this way we can control our data. Also we can control it also via our terminal. So we can go to the robot and watch topics published by ROS. For this purpose we can run ROS topic echo ultrasonic ROS2. Oh no, sorry, ultrasonic range, and we see that packages. Each package contains header with timestamp and also with their values, max range and range. And we see if we start to move obstacle in front of robot, move it closer or far away from the robot, these measurements are changes. So in this way we can also monitor our data either or via terminal, or via Chrome. Okay, let's back to our presentation. Next one, we should run our obstacle avoidance node. For this purpose we need to go to new terminal and run ROS2, run obstacle avoidance, laser obstacle avoidance. This package run obstacle avoidance node and publish ultrasonic, publish SIMD-Val and SIMD-Val smooth topics, and we can watch how it looks on the Foxglove. For this purpose we can split this panel. For example, here we are, and add SIMD-Val SIMD-Val linear X. Blue line means the speed, forward speed. And also we can add SIMD-Val angular Z. So blue line means forward speed, how fast robot move forward, and orange line display the angular velocity when robot turn right. And now we see linear X equal 1 and angular Z equals 0 because distance is 100 centimeters. But if we decrease distance, for example, now it approximately 20 centimeters, we see that angular X becomes 0, linear X becomes 0, so robot stop move forward, and orange line angular Z becomes 0.5, and it means the robot start moving to the right. And if we increase distance above 50 centimeters, we see that orange line becomes 0 and blue line becomes 1. So this is the algorithm, obstacle avoidance algorithm, that read measurement from the ultrasonic sensor and send commands to the robot motor driver how to move it forward or turn left or right. And we see ultrasonic publisher topic and obstacle avoidance. Obstacle avoidance read ultrasonic range data and send SIMD-Val, no, need this, sorry, SIMD-Val and SIMD-Val smooth. These two messages that published data for motor driver. Okay, let's back to our presentation, and we can also check this topic, ROS2 topic echo, and name of the topic, SIMD-Val. Yeah, we see that packages linear X, angular Z. Now we see linear X equal 1, angular Z equals 0. It means more robot moves forward. If we decrease distance, we see linear X becomes 0 and Z becomes 0.5. So as in case with the case of the ultrasonic, we can also watch visualize our data either or via Foxglow or via command line, via terminal. Super. Let's go.
Alexei,
Yeah.
sorry to jump in, but there is a great question in the chat I'd like to share. If you don't mind, could you please show the ultrasonic sensor and its changes on the camera so we can see it, how it measures distance? Thank you very much.
Sorry, I didn't catch it.
So could you please show us how the sensor is seeing the distance between your hand and the robot?
Okay, let me, I will show you. You mean, for example,
we just want to see it on the camera, like for visualizing.
Yeah. Let me show you. This is my robot. Yeah, this is my robot. Yeah, this is my hand. And we see if I how it's, oh, okay, this is, where is it? This is distance sensor, ultrasonic. Okay, this is my hand, this is measurement. If I try to move my hand closer to the sensor, we see that this line is decreases, yeah. And if I start moving from my robot, it start increasing. Is it clear enough for you?
Thank you very much. Yes, it is.
Good. Okay. So we go to our main part is to turn our robot. Next one is to run motor driver. For this, we should open new terminal. Not this one. No. And run this ROS2 run motor driver. CMD well subscriber. But before it, we should turn on our robot. It's turned, and put it on the track. And check, let me check. Oh, okay. And I will switch my camera. Okay, this is the robot on the position. I will run the motor driver, and we see how it start moving. So this is the how this algorithm works in real life with the real robot. Let's switch back to our presentation.
Before we move on, we have another relevant question here. So can you please explain, does brightness impact the ultrasonic sensor behavior?
Brightness. Could you please rephrase it?
Any sources of light can impact when
No,
your
no, no.
lamp is
It's
on?
because it's ultrasonic. It's sound. So it not depends on the light. It can work in night without lighting because it's a sound sensor.
Thank you very much.
Okay, so let's back to our presentation. Yeah, first one is the couple of words about the environment. First one is topic graph. Our robot need to publish 3 topics: ultrasonic range, to publish distance that this ultrasonic sensor measures and publish it. Second one is obstacle avoidance. Note that subscribe to this ultrasonic data and publish linear and angular velocity. And third one is the motor driver that subscribe to the velocity controller and convert commands to the motor wheels. How we see on these plots. Ultrasonic. It's switch off. We switch off our motor. Okay. Second one is the about smooth velocity control. We have an idea that we have a robot and wall. And we have some point when we should stop our robot to prevent it hitting to the wall, for example 20 centimeters. But to avoid situation of abrupt stopping, for example it moving forward, but then when he reaches the 20 centimeters distance to the obstacle, it stops rapidly, so it's not very convenient. So we make some smoothing with logarithm function. It means, for example, if we reach distance 80 centimeters, we start to decrease velocity smoothly, and when it reaches distance 20 centimeters, the linear velocity becomes 0. We can see it on this plot. Let's take this history. Oh, sorry, I didn't share it with you. For example, this real example. Where is it? Oh, let's check it here. Let's increase it a bit. Oh, it's not linear, but let's replace it with the velocity smooth linear x. We didn't see it because we haven't recorded it. Okay. but we understand that this smoothing is very convenient approach to move our robot more smoothly without abruptly starting move forward or starting move backward, stopping abruptly, and so on. Second one is the Kalman filter. The main idea, let's back to our Foxglove and see this bottom plot is the measurement. Let's recall, this blue line is the raw measurement from ultrasonic sensor. And we see that it has some kind of rigid lines. It means that measurement has some noise because it was, for example, 73 centimeters, and then it becomes 85 centimeters, but we understand that this distance couldn't be changed so abruptly. So we need some kind of algorithm that will add kind of smoothness for this measurement to reduce noise, because any sensor produce with the real signal, it produces some kind of noise. Okay, let me show you. No, not this one, but this one. So Kalman filter, how it works. For example, we have green line is our real signal, this smooth line. Blue line is the noise signal. Its signal represent our signal from ultrasonic sensor. It always noisy, like this, like this blue line. And orange line is the signal from ultrasonic sensor that was reduced from the noise, cleared from the noise, and it more similar to the original data. And we see that this orange line is more close to the original line, more close than this noisy signal, blue line. But we also see the problem with this cold start problem, because Kalman filter predicts data depending on the previous data, but when it starts, it has lack of previous data, so it produces wrong data. But after a couple of seconds, it gather enough information and make correct predictions and start to give real data. So we also implemented in our algorithm, for example, this obstacle avoidance. We implement this data, and in ultrasonic publisher we implement the Kalman filter. We read data from ultrasonic sensor, we correct it, make prediction, and write to the message data filtered by Kalman filter, and we see results on our Foxglove. So at the bottom line we can use also either raw data from ultrasonic sensor or data filtered by Kalman filter, but usually any data produced by any sensor are filtered by Kalman filter. Moreover, most sensors, most controllers has built-in Kalman filter and provide data almost filtered by it. Okay, let's back to our presentation. That's all. This is the end of our presentation. But before to finish our lesson, let's discuss a couple of topics. First one is the difference between simulator and real robot. If you don't have a robot, you can learn the robotics with the simulator. You can use simulated robot to implement this obstacle avoidance algorithm, another algorithm, but you should take into account small differences between simulator and real robot. One difference is inertia. For example, if you implement your obstacle avoidance algorithm and set minimal distance to the obstacle to 20 centimeters, it could be okay for your simulator, but if you try to implement it on the real robot, this distance could be a bit small for real robot, and it could be it couldn't stop because it has its own inertia, so you should increase your distance. In our example, we use distance 50 centimeters. Second one is the low velocity. For example, if we go to our plot, we can see that some data, not this, let me back this SimDevel linear X. When, for example, angular velocity becomes close to zero, your motor can stop responding and your robot can stop. So low values of velocity can lead to stopping your robot. So you should not only include velocity 0 or 0.5 or 0 or 1.0, but you also check if it close enough to 0 and avoid this situation. And last one is reflection. For example, if your robot goes to the obstacle at the low angle, if reflection angle is low, then its signal from ultrasonic sensor couldn't be returned to the sensor back, and robot can erroneously think that there is no obstacle and hit the wall. So this is a couple of issues and topics, tips and topics that you should remember if you try to implement your simulator or move into the real robot. And at the end of this presentation, let me thanks for the help. First one is the robot operation system that helps to create programs for the robots. Foxglove for visualizing data from robots. Next one is the Gazebo. Gazebo is the most popular robot simulator. So if you don't have a real robot, you can start with the Gazebo simulator. It totally replaces your robot with the simulated data. And Deconstruct is the educational platform that helps people to learn robotics. So this is the end of presentation. This is the end of the lesson. We can answer on your questions if you have any of them. Max?
So right now we don't have any questions on our LinkedIn live stream, but we have our live audience that are with us on Google Meet, so they can ask some questions with their voice if they want to. So let's wait a couple of seconds.
Okay.
Okay, yeah. Hello, guys. Do you hear me?
Yeah.
So, yeah, I have a question about moving through the floor, and not about the obstacles, but about the missed floor. For example, while you moving through your apartment, yeah, and you don't see that it is stairs, and you can, I don't know, go through the stairs too quickly and drop your car. So how we can deal with this situation? Can we check like missing floor, or maybe ultrasonic sensor with maybe with some I don't know, maybe change it angle and get information from the bottom of your car, not only from the forward. Yeah, what do you think about this?
Yeah, actually, this is the simple example how to make a robot knowledge about environment, like walls, obstacles, stairs, etc. Nowadays, we have more precise and more interesting sensors like LiDAR. This is the LiDAR provides robots more broadcast information about environment. Also for the understanding environment like stairs, obstacles, we need different kind of sensors. For example, to check changes in the height, for example, stairs or other obstacles, we can install a set of sensors on the robot's body. So, for example, we should install a couple of ultrasonic sensors at the bottom of robot, in front of the robot, that points to the bottom to detect stairs. For example, if it moves forward on the floor, it see that distance is short enough, for example, a couple of centimeters, but when it goes to the stairs, the distance increases, and so the robot understands that it has close to the stairs. And LiDAR helps to understand robot that angle is too short, too low. For example, if ultrasonic can skip signal, if angle to the wall between robot and wall is too small, the ultrasonic sensor can skip this signal, but LiDAR provides the measurement not only in front of robot, but also it can provide information about different angles, including 360 angles.
Degrees, yeah, I got you. Okay, thank you. Thank you.
Okay, anybody else?
Can you hear me?
Yeah.
Yeah. I just for this example that you mentioned, like the simple algorithm. I understand this is just the simplest possible algorithm, but just even with this algorithm, it's super easy to get robots stuck into a room because obviously it cannot pass any tunnel like obstacles because it will spinning endlessly, always seeing the obstacles, right?
Yeah.
Because it's spinning in one direction, it should be spinning in also in opposite direction.
Yeah.
From time to time. So is there like a standard algorithm that's works for all situations in one dimension at least? There's like a simple one, not requiring some machine learning or sophisticated visuals, computer vision. Do you know some?
Yeah.
Maybe.
Yeah. Actually, in nowadays robotics, we don't need to implement any kind of algorithms because a robot operation system has set of packages, set of modules for solving different tasks, and obstacle avoidance is the one of the most widely used. So all you need is to install this robot operation system and include this package. Just install it, connect it, and set up ports, which kind of sensors you have, and this package will automatically navigate your robot without implementing these algorithms. So this example was just demonstration how to use a real robot with robot operation system with small programming skills to start your simple implementation of simple algorithm. But in real life you already have those packages and you don't need programming anything.
Yes, thank you. I have another question regarding. I think it's very important to mention that ROS is not designed to work on real-time operation systems. So it can work on our classic desktops, right? Like on computer or Raspberry Pi. But is it like when we need a real-time like system close to real time when the time matters? Is there any alternative to ROS or there are some ports that can work on a real time system?
Yeah, I'm not agree with your statement because robot operation system is most commonly used and real-time operation system. Moreover, NVIDIA has its own ISAC development platform that works on the hood. It run on the ROS, and moreover, NVIDIA drivers has announcement in 25 years its own driver system. This driver system used, for example, Nissan, Toyota, Honda cars for development and autonomous driving. And I believe drivers has the ROS on the hood.
Yeah, interesting. Because like I had an experience with STM32 or like low budget systems. They they don't have stable version of ROS.
Oh, yeah, it's actually you're right. It's a big problem because this robot operation system is mostly work on this operation system like Ubuntu, and in our case, we installed Ubuntu on Raspberry Pi. We don't install Raspbian operation system. We install Ubuntu 24, and because ROS is not completely work goods on the Raspberry Pi Raspberry operation system. And NVIDIA has its own build for ISAC. This robot ROS built it for NVIDIA platform.
But the ROS is open source, right?
Yeah.
So it's probably a fork. Yeah, that's all. Thanks.
Anybody else? Okay, we have a couple of minutes to the end of our workshop. I hope this lesson was very helpful for you, very interesting. At least we have gained momentum how real robot works, what kind of platforms it uses, what kind of software it uses, how you can start to diving into it, which programming software you need, some kind of basic knowledge about robotics. Okay, so let me say thank you for your attention.
Thank you.
Thank you too.
Yeah, guys, so thank you all so much for joining us today. We really appreciate your time and all the great questions you shared. It's been a pleasure having you with us, and if you enjoyed the workshop, make sure to follow us so you don't miss out on future sessions, because we've got more exciting topics coming up, so stay tuned. And also, by the way, you're welcome to access the repositories that were used during this workshop. Just reach out to us, LinkedIn, or at our website, flyapps.com, and we'll figure it out for you. So until next time, take care and see you soon.